Patent number 821,393 was registered by the Wright brothers in 1906, achieving what was thought to be impossible for centuries. The 22nd of September 1946, aircraft DC-4 went a step ahead, completing the first transatlantic flight in history of humankind. The airship was, indeed, one of the most successful inventions of all times, yet numerous inventions preceded and followed it. Leonardo da Vinci's flying machines, or the Soviet Ekranoplan, for instance. This is just an example of how an idea can lead to many inventions and life dreams. When it comes to city development, many worlds have been dreamt in movies or in literature, and one of the key aspects for this is vehicles itself. Leaving whether flying cars will be a reality apart, many upgrades to existing cars can be thought of. So, what if we simply put a propeller on all our cars? A few years back, in 2006, Rick Cavallaro and his team proposed a wind-powered vehicle that would exceed the wind speed that was powering it, settling an internet debate to decide whether it was violating the laws of physics.
We said, okay, if we build a little model of one and put it on a treadmill, that just puts it to bed.
Right. And it worked really well.
Now you're holding it back with the score.
Hey, Mississippi? Yeah, I'm keeping it from coming forward, otherwise it'll fly right up the top of the treadmill.
Even physics professors were arguing that the treadmill wasn't a good analog of the real world. I'm like, literally day one physics is inertial frames, right? It doesn't matter if you're moving or the air's moving. Others were saying there's magnets, there's wires, there's fans out of you. So then we do one showing,
no fans.
The curtains aren't moving and stuff. And finally he says, we got to build the real thing.
On 24 March 2010, the team created a vehicle named Blackbird and proved it to be possible. And yet, after a few achievements, the debate was far from over. Why it worked seemed to be still debated. In 2021, University of California, Los Angeles physics professor Alexander Kusenko disputed the claim, having seen a YouTube video on the Veritasium channel by Derek Muller. Kusenko and Muller entered into a $10,000 bet that required Muller to prove the validity of the claim, which was witnessed by noted scientists Neil deGrasse Tyson and Bill Nye. Muller won the bet, to Kusenko's satisfaction, with a series of model experiments, investigation of the original supporting data of the Blackbird run, and exploration of the supporting equations. On a simple way, the device works because wind powers it and its wheels spin the blades, which makes a greater acceleration, surpassing wind speed. To say that Blackbird's approach is the implementation of propellers on cars is completely false. Though it surely is focused on the practical part, let's remember its popularity arises from controversy, but that is not entirely true. Despite it not being attractive for a daily use, I'll refer to what I said in the beginning of the video. An idea can lead to many inventions and life dreams, so why not play around with equations and simulators? Because this image surely seems attractive, doesn't it? Well, maybe not. This is a model of Cavallaro's Blackbird. Adjusting the wind speed, the mass of the vehicle, the propeller radius, and the surface area of the vehicle, which for the sake of simplicity is the same in the front and in the back, the program is able to calculate how long it would take for the vehicle to reach a certain speed. Of course, this problem is very much more complex than this, having to consider numerous aerodynamic measures which a 17-year-old student cannot calculate on his computer. That's why the speed of air moved by propeller is less realistic. I took a formula by one of the NASA's departments, which is used for playing propellers inside plane engines. So propeller blades are very complex. They are not a horizontal metal sheet, but rather they have an angle which varies on every point of the blade. They have irregular round edges, and the only way to calculate their thrust is either an aerodynamic study with a complex program and fluid knowledge, or an approximation to the problem, as I did. Of course, you could equal wind speed to this variable, which is virtually impossible, and the result is unsurprisingly infinite. This tool should not be considered an absolute truth, but rather an approach to measure the efficiency of the system. For example, lowering the radius to 0, will allow us to compare a vehicle that has a propeller with one that hasn't. Having explained the validity of the program, I'll explain every formula that has been taken into account. After some research, I came up with this formulae. The key part here is the famous formula for non-conservative work. Using this, we get that the final mechanical energy minus initial mechanical energy equals sigma force times displacement. Initial mechanical energy equals 0 since velocity is 0, and the final mechanical energy equals 1/2 by mass times velocity squared. There is only kinetic energy. Leaving apart the displacement, we have the final solution, except we now have to work out which forces apply to the problem. These are the force exerted by the wind on the back causing the acceleration, the opposite force, which is the wind drag formula, and finally the force exerted by the propeller. You might notice I didn't take friction into account, and that is because wheels roll. Ideally, they shouldn't lose energy, and how much they do is very difficult to calculate. After some research, it turns out every wheel has different properties, which every brand doesn't like to show for some reason. And again, these properties are entirely practical. They are not calculated by experimentation and not by mathematical calculation, so I cannot do much. Now let's go back to the formulas. Drag formula is not very complicated, except it is a simplification of a much more difficult task, because you need the drag coefficient, which is experimental again. I know a plane sheet has a drag coefficient of 2, and I could have used a sail that propelled the vehicle too, but that's impractical and ridiculous. Instead, I made a drag coefficient for my vehicle, considering the usual numbers of commercial cars. I decided it was 0.5. The applied force by the wind uses the same formula, which, if you think, makes you understand it. It just calculates how much force the wind exerts. But this has a catch. The velocity on the applied force formula is equal to the velocity of the vehicle minus the velocity of the air powered by the propeller. The drag formula's velocity is the wind speed minus the speed of the vehicle, which we take the half of the final velocity. Both consider an air density of 1.09 kilograms per meter square. The final formula is the one mentioned earlier. It only takes into account the difference in air pressure and has a similar shape to the ones earlier. Then it is multiplied by the surface of the blade spinning. This is the whole program, and I hope it hasn't been too confusing. I know I simplified lots of things, but I just hope I made something somewhat useful. Thank you for watching.